Turing computable functions. I will just remind us of the definition. So a function that looks like, f, where usually I like to say the domain and the codomain here. This is a function which takes some strings and gives you some strings as the answer. I'm going to write that like, well, it would be like this, right? This would be sigma star, meaning the set of all possible strings on your alphabet sigma. So if you have a function which takes some string as its input and then gives you another string as its output, this is called Turing computable. If there exists a Turing machine which performs F on the tape. That is to say, i.e., the tape starts with some string x and then finishes with whatever f of x is. That's what I mean by the Turing machine performs F on the tape. It means whatever you start with on the tape, if that's x, then the machine will do some stuff for a while and then stop, and what ends up on the tape is f of x, the value of the function. And we did some very simple examples last time of Turing computable functions. Things like, f of x equals ax. That's a function which takes any string and just puts an a on the front of it. Can you do that with a Turing machine? Yes, you can. The machine would move one position to the left from the beginning and change a blank to an a, and then that's it. Or you can put, if you want to get fancy about it, you could put a bunch of stuff at the beginning and then put, some stuff at the end too. That's also Turing computable. That's a little, slightly more complicated. You would move to the left 3 times and then write A, B, A, and then move all the way to the end and write B, B, something like that. All right, these are examples of Turing computable functions. These are what kinds of functions can a Turing machine do. I had a couple of fancier examples because those ones that we did last time, in my opinion, are quite simple. So I want to do 2 more fancier examples using strings, and then I want to talk about more traditional style mathematical computations like adding numbers and such. But let's do a few more interesting strings. Can I just say sometimes our domain of the function isn't all of sigma star. The domain of f, as I wrote it up here, f is a function at the top there, goes sigma star to sigma star. That means you can plug any string into it and you get any string as the output. Although in many examples, you don't want to allow your function to have any possible string as its input. There are many examples where you just want a certain type of strings as the input. Sometimes our domain isn't all of sigma star. Often we consider functions like f goes, say, some other set to sigma star. F goes s to sigma star, where s is some subset of sigma star. That is, you don't necessarily need the function to work on any possible input. It only works on certain sort of useful inputs, or inputs which have a certain format to begin with. All right. This is like when you're writing a real-life program in a real-life programming language. The compiler is not supposed to do stuff no matter what you type for your code. Your code has to somehow obey certain structures to it. And so the domain typically is not all possible strings, but it's some subset of strings. Anyway, let's try an example like this. How about, here's an example where S, the domain, is b to the n, a, b to the n. So this is an example where you always start with a string that looks like that to begin with. And the function goes, f takes something like that, b to the n, a, b to the n, and then gives you b to the n, a, b to the n. It sticks another a in there. That's what it does. So this is a function which begins with something like b to the n, a, b to the n. It has an a in the middle, and then the answer is like that. It puts an extra A in the middle, a second A in the middle. All right, let's see if we can do this with a Turing machine. So you assume that the tape begins like that, and then you change it so that it looks like this. Anybody want to suggest how we could do that? There's one thing that you will immediately realize when trying to make a Turing machine that does this. I think the natural thing to do is, can I just like, when I see this, I have to start at the beginning, but I'm basically going to pass over this b to the n. This doesn't matter, and I want to leave it the same in the answer anyway. So really, I want to pass through this b to the n. Once I see this a, I think the most natural way to think this through, and this unfortunately doesn't really work, say, how about I just like stick an extra A in there and bump the rest down the line a little bit. You can't really do that on the tape of a Turing machine. The only thing the Turing machine is allowed to do is change what it sees on the tape in one spot. It cannot somehow insert a new little spot into the middle of the tape. That's not allowed for a Turing machine. Anybody have another suggestion? I mean, you can do like vaguely something like that, but there is no such thing as just push the rest down. Yeah? Yes, so this is a great idea. She says, rather than thinking about pushing these guys down one spot, actually they're all B's anyway, so you don't have to push them down since they're all the same as each other anyway. Her strategy was change the first B here to an A. That will give you this A. And then you'd be missing a B at that point, so then you just go to the end and add a B at the end. All right, so that's the strategy. I will try to write something like that down. The strategy is change the first A here to B, and then add a B at the end. And I think that basic idea sounds good to me. Change the first of those B's to a. Change the first of those B's to A. Did I say that? Change first A to B. Yeah. Then add B at the end. All right. Let's see if we can do it. So I'm going to do this below the page break. I don't know if anybody cares. Here's my starting state. Change the first A on that block to B. So first you have to move the head to the right a bunch in order to get to that spot. So I'm going to move to the right through a bunch of B's, and then move to the right through one single A, and that will land me where I want to be. So the moving to the right through several B's will look like this, BBR, like that. And then through one single A looks like this, AAR. So that one will move me through all the B's first, and then eventually move me through one A. Okay. Change the first A to a B. Anybody want to suggest what that should look like? What you got?
I did BAR, and then I did another one for blank.
BAR, okay. So, and this is an arrow to a new state?
Yeah.
Yes, I agree. BAR. Great, this will change a B to a A. Now he said we also did something for a blank. Why do you want to consider a blank?
Because there could be no B's.
Yeah, if the n is 0, then you may need to turn a blank into an A. I guess if the n is 0, then you need to, you still need to put two A's in there. So this is a good idea. Blank, A, and R. Is that also on the same arrow? The label?
State, but I guess it could be.
Yeah, I think you may need a different state. Can we just ignore that case for now? But I'm gonna put that as like a little spur here. We'll have to separately consider what happens if there were no B's. What do you have to do in that case? That's sort of a technicality. Let's just try and finish off the reasoning for the sort of the top route. This is the one in which ordinary things happen when you see when there are some B's in the string. Okay, I changed the first A to a B. What? I wrote this wrong. I meant change the first B to a A. Yeah, I confused myself briefly, but then convinced myself it was all right. It was not all right. Sorry, I think everybody knew except me. Change the first B to A. And that's this step right here. Change the B to A. Okay, now add a B at the end. That means we have to move to the right again through all of these B's until we see a blank. and change that to a B. So I'm going to go BBR here. This will move us to the right through all the remaining B's. Finally, we will arrive at a blank at the very end, and we want to change that blank into a B. And I think that'll do it. Actually, I don't need an accepting state. Remember, in a Turing machine which is meant to compute a function, there typically is not an accepting state. You just stop after a while. And that's the end of it. Yes?
How do you ensure that there's the same number of things at the
That is already guaranteed by the way that the function is set up.
Oh.
So this just says you can assume already that the string looks like this, and then you have to turn it into this. Yeah. So this is a good question. You don't actually have to make sure that this amount of B's is equal to that amount of B's, which we didn't actually do that in here. All right. Great. What about this this sort of lower leg here? That is if this will happen if there were no B's at all. In that case, we see one A, we make another A. I think in that case we're done at this point, right? There is no more to do, and so I think I can just do that and say you should stop. Right? This is sort of the this is the special case. This only happens if n equals 0, right? If there were no B's at all. I think it does require another separate case. A separate state right here, because if you just continue onto this state with an arrow with that label, then it will still continue and write another B at the end, which you wouldn't want in this case. All right, excellent. So this is a function which does this, inserts an A in the middle. Like I said before, inserting an extra letter is not really a natural thing that a Turing machine can do well, at least not in a single step. You cannot insert a letter. Here we sort of got lucky because this thing over here is all B's anyway, and you can just tack one onto the end. Here's an example, though, where you really have to do a bit of work about it. So let's say in this one, I begin with something like XCX, and I end with XX, where X is just A's and B's. All right. So this one has a thing in the middle. All you got to do is just remove the C, which sounds easy, but actually for a Turing machine, this is not terribly easy, because there is no such thing as removing a letter from the middle of a string on a Turing machine. The Turing machine can change it to a blank, but that's not what you want to do here. You want to actually remove it. Anybody got a suggestion for that? Yeah.
You make it into an X and then remove the last X, or make the last X inevitably.
You have to remember the X's are strings, right? It's not just a single letter. If the X was a single letter, then what you said would be exactly right. Although that is much easier than the situation we're in here is something like A B B B C A B B B, right? That's kind of what we're looking at here. And this has to be transformed. Maybe I'll into this A B B B A B B B without the C in the middle. Anybody got an idea? Yeah?
Could you honestly just go to C and
Yeah.
write blank after that entire thing and then just copy the first section after?
Okay, yes, I think that would work. That would be difficult.
Yeah.
What I have in mind is a little easier than that. What's difficult about that, actually, to write a Turing machine that just does this, this is not easy on a Turing machine. You can do it, but you have to do you would have to do several intermediate steps where you say, I have this A here, I'm going to copy it over there.
Mm-hmm.
You would end up, first of all, with a string like that. Then you would say, go back to the beginning and find the next letter that I want to copy, which is actually the B, it's not the A anymore. In order to tell the difference between that, you'd have to mark this one so that you don't copy it again. But then you would end up with, actually what you end up with is that, and then you have to go back through and unmark everything. It can work, but it's a pain. What I have in mind for this is a little easier than that. Anybody have another idea? How about, here's my idea. Take the C away, and then these guys, one by one. So maybe start off by making the C blank, or actually it doesn't matter, you can just leave it like it is. One by one, take this arrow and copy it one spot to the left. And then copy each of these one spot to the left. So the idea is this guy will end up there, this guy will end up there, there, and there. That's going to work. And you don't even have to look at the first half of the string, really. It doesn't matter. So I'm going to leave the first half of the string like it is. So the first thing you do is easy. You just move to the right until you see the C. And then that's when the real action starts. So I'm going to, can I write like in words my strategy here? You should, so after the C, just leave everything the same before the C. After the C, you copy letters one by one. One spot to the left. All right. This involves a lot of individual moves to the left, which, as I said before, I don't really like moving to the left, but you got to do it. All right. The alternative could be you could also start at the C and then backtrack and copy each letter to the right by one position. You could do that if you want, but these would be equivalent. Anyway, that's the idea. How about, let's see if we can do this. First of all the action happens after the C. So the first thing I'm going to do is to just move to the right until I get to the C, because nothing interesting happens until you get to the C. So I'm going to go AAR, BBR. Moving to the right until I get to the C. When I do get to the C, I'm just going to leave it as a C for now, although it's not going to stay a C forever. But I'm going to leave it as a C. Eventually this C, like in this example as I've written here, this C will become an A, but actually I don't know yet that it's going to be an A because I haven't seen what this letter is. So I would just leave it as a C for now. The pattern is going to be I move to the right one position, copy this, sort of have to remember what this A is, move to the left and change this letter to whatever the A is. This will involve two branching paths, kind of like the examples that we were doing last time, because your behavior depends. If this letter here was an A, then you want to put an A one spot to the left. If it was a B, you want to put a B one spot to the left. So this is the classic sort of two branching paths, depending on if the next letter that I see is an A, I'm going to do AAL. If the next letter I see is a B, I'm going to do BBL. All right, the L because I sort of, look at this A, realize, okay, that's an A. I'm going to go back to the left and stick it here. What do I stick here? It's going to be an A. Now, what it used to be, it could be a C, or it could have been an A or a B if I'm in like later steps of this copying to the left. So there's going to be, and actually once I do that, I'll be done with this branches. This is a very simple kind of branching, but this will say CAR, AAR, and BAR. That means no matter what it is in that spot, I want to make it a A. So it could have been a C, or it could have been an A or a B. In any of those cases, I make it an A. And then move back to the right again. And now I will be pointed at, after moving to the right again, I will be sort of pointed at the letter that I just copied. And now I want to make this into a loop by going back here and saying something like AAR, BBR. Because when you're in this state, you're looking at the letter that you just copied, which you don't care about anymore. You move one step to the right, then you'll be pointing at the next letter that you want to copy in the next step. All right, so this is my basic loop here. My other branching path is like this. BBL, so this would be when the letter you're going to copy was a B. You move back to the left, and then you, no matter what you see there, you change it to a B. CBR, ABR, BBR. That'll do. All right? Eventually, you will do this over and over again. Eventually, you'll get to a blank. That will happen in this position, I believe, and then it'll just stop because there are no arrows involving blanks, and so the machine will halt, and it'll be done. All right. Any thoughts about that? There is one special case actually that this diagram does not handle, and that would be if this X is the empty string. That is to say, the whole thing is just a C. What will happen if the whole string is only a C? It'll do this arrow first, and then it will get stuck here because it'll be looking at a blank. But actually, if it's just a C, what you would want is to end up with the empty string, right? The C is supposed to go away. So just to handle that is if you are in this state and you see a blank, I believe this will work. This is what it says on my paper. BBL here. That is to say, if you see a blank right there after the first C, it means that there was no X at all. What you should do in that case is just wipe out the C and leave everything as blanks. So here I say C, C blank. C, C blank. What? C blank. And then R or L or whatever. C blank R. And that's it. All right, this is the case which happens when there was no string at all, no X at all, just the C on the tape. You erase the C. All right. All right, I'm feeling good about that. That was kind of complicated in my opinion. I said I would like to, so these have been string functions, right? Functions where you start with a string, like A's and B's, and you do some stuff to it. All these examples that we've done have been Turing computable. That's because you can do them on a Turing machine. Is there such a thing as a function which you can't do on a Turing machine? This is something that you should think long and hard about. Something that should trouble you while you're trying to fall asleep at night. Are there mathematical functions that you just couldn't possibly do on a Turing machine? Something to think about. We will talk about this eventually, but not today. I want to talk about simple, more traditional mathematical functions involving like numbers and adding and multiplying, that kind of thing. So let's talk about simple numerical functions. When it comes to numbers, as we've seen already, it's going to be easiest for us to handle binary numbers just because they are easiest to handle as strings. If you're talking about binary numbers, then the only possible digits are zeros and ones. And so the alphabet that you're considering only has 0 or 1, and your machine has to have arrows for zeros and arrows for ones. That's it. Whereas if you're doing a more traditional sort of human legible base 10 numbers, your alphabet has to include all the digits 0 through 9, and then there's many arrows you have to handle. I don't want to get into any of that. It's possible to do, but it's a real pain, and there's actually no good reason to do it other than like culturally because we like base 10 numbers. So we are going to do everything in binary just because that's more convenient, and of course you probably know that's really how real computers do everything anyway, because it's easier that way. So simple numerical functions. How about, so if x is a binary number, that is to say, I imagine, like 1000. This is the number 8, right? Or is it 16? This is the ones digit, the twos digits, the fours digits, the eights digit. So this is the number 8 in decimal. decimal means, base 10. Binary means binary, base 2. So that's a binary number. You think of this number as being written out on the tape, digit by digit. So the tape says 1, 0, 0, 0, and then, a bunch of blanks after that. Can we do some simple kinds of mathematical functions, simple like arithmetical things? Let's start with a very easy example. How about f of x equals 2 times x? Can you multiply a binary number by 2? The answer is yes, you can. If you think about this, actually multiplying a binary number by 2 is very easy to do. Anybody happen to know how to do this? Like if I have a binary number like this, I don't know off the top of my head what base 10 number that is, but how do you multiply a number like this by 2? In binary? The wrong answer is convert to base 10, then multiply it by 2, then convert back to binary. You shouldn't do that. Yeah,
Put a 0 at the end.
Put a 0 at the end, yeah. Just like in base 10, to multiply by 10 is easy. You put a 0 at the end. This has the effect of increasing the exponent on all of the other digits. The tens digit becomes the 100ths digit, and so on. That's multiplying by 10. In binary, it's similarly easy to multiply by 2. You just add a 0 digit or bit, a binary digit, to the end. Right? This is how you multiply by 2. So that number would become, the same number again with an extra 0 on the end. That's how you multiply a binary number by 2. Can you make a Turing machine that does that? Yes, that's easy. I mean, it's like the examples that we did yesterday. So a Turing machine that does that would be something like, we have to add a 0 at the end. That means you move to the right through any 1s or 0s that already exist, and then as soon as you see a blank at the end, you make it a 0, and then you stop. So this is basically the same as examples we did last time. I begin by moving to the right through any actual digits that already exist. When I get to the end, it'll be a blank, and that blank I turn into a 0, and then stop. That's all. All right, this adds a 0 on the end of a number. So a Turing machine can indeed multiply a number by 2. You can tell your mom what you learned today. I learned that a computer can multiply a number by 2. It's true. What about, let's try something a little bit more interesting. To your mom, this might sound easier. It's actually harder. What about f of x equals x plus 1? Add 1 to a binary number. For example, if x is something like 11011010, then x plus 1 is, any masters of binary out there? How do you add 1 to that number? Yeah?
Just the 1 at the end.
Yeah, you turn the 0 at the end into a 1 at the end. Yeah. We are in the presence of a master of binary. All right, this is how you add 1 to a binary number. I said this is actually hard. What's hard about that? Actually, that was an easy one. What's hard?
Try, I think, one of the best ones.
Yeah, if there's already a 1 at the end, then you got to carry, right? Which is something that, a third grader might find hard. This is slightly hard. You have to sort of retrain your mind to carry properly in binary. So here's another example. If x is, maybe I'll just write, I don't know, like that, say. What is x plus 1 that now? So I'm going to try to actually write this the way that I would write it as a third grade. I don't know when people learn to do this. Third graders? I don't know. I don't know any third graders. I used to, but they're older now. All right, how do I add 1 here? You got to carry. Now, when I'm adding this in binary, I go 1 plus 1. That's a carry, so I put a 0 here, and I carry the 1 by writing a little guy up there. And now this is going to be a 1 plus 1. That's another carry, because you'd be tempted to write 2, but there's no such thing as the digit 2 in binary. Once you get to 2, you got to carry. So this is a carry. I put a 1 there. You can carry a little 1 there. This is another carry. What? I don't put a 1 there. Sorry, it's a 0. I said 0, but then I wrote 1. I put a 0 there because 1 plus 1 is 2, which in binary looks like a 0 with a carry. And then again, I have a 1 plus 1, which is 2, which is in binary looks like a 0 with a carry. And now I have 1 plus 0 is 1. And now actually the my sort of nightmare of carries is over, and the rest of it can just copy as it used to be. So this was a 1 plus 0. The carry is now over, and then everything else can stay like it is. So this is a 0, a 1, and a 1. I hope that that made some kind of sense. This is adding in binary, adding 1 in binary, all right? You got to carry sometimes. Can we make a Turing machine that does this? I think we can. I want to try to make a Turing machine that does this. I would say, so my first very basic observation is everything happens on the right end of the string, right? This is something that you know when you first learn about how to do this. When you're adding things together, you start over here. You don't start over here. So on my Turing machine, I'm going to have to move all the way to the right just before we do anything. All right. Why are numbers written in such a way that you have to process them kind of from right to left? I believe this has to do with the fact that our number system was basically invented by the Arabs, and they write Arabic is written right to left. And so this kind of thing, which seems somewhat unnatural to us, is actually natural to someone writing in Arabic. Anyway, so my Turing machine to do this is going to begin by just moving to the right forever. 0, 0R, 1, 1R. Eventually I get to a blank, I go BBL, and now I'm ready to start. So that's just sort of, actually almost all of our mathematical functions of this type are going to begin with that thing that you see right there, because we have to move all the way to the end, the rightmost end of the string of numbers to start doing anything. Okay, and now I am basically going to have two separate states here. One which involves carrying stuff, and then eventually you'll be done carrying and you can sort of end the computation. And I would say actually what I just described is maybe more complicated than it has to be. Just think about, I'm trying to add 1 every time. So if I see a 0 at the end, it should become a 1, and that's it, right? So I'm going to say this is kind of like the best case, is that if what you see on the number is really a 0 on the rightmost end, if it's really a 0, you just make it a 1, move to the right, and stop. So this state is not going to have any outgoing arrows. What if it's a 1? Think about what happens if you see a 1. So that's the carry situation, all right? If I see a 1 here, first of all, what am I going to write onto the tape? That is the answer. What's the answer in this digit if I see a 1?
0.
It's a 0, right? Because I'm adding 1 to it. So if I'm in this digit and what I see is a 1, the answer should be a 0. So there's going to be an arrow down here that looks like 1/0, right? Because if what you see on the tape is a 1, the answer should be a 0. Then you should move to the left because a carry needs to propagate to the left. So actually the arrow is going to be like that. Now, where does this arrow go? Is it going to go to yet another state, or is it going to be a loop back arrow? Actually, this seems simpler than it, this problem seems a little more complicated than it really is. Because actually that is my final answer. This is really all you need to do. Let's try and think about why that actually works. What it says is, if you see a 1 on the tape, what? I don't know what that was. If you see a 1 on the tape, your answer in that digit should be a 0. Then you move to the left, and you basically just do the same stuff. If you still see a 1 on the tape, the answer in that digit is 0. You continue moving to the left. If you still see a 1, the answer is 0. You continue moving to the left. Eventually, you get to a 0. That 0 now should become a 1 because of the carry. And that happens right here. That 0 becomes a 1 because of the carry. So actually, this works perfectly to address this situation here. All right. The way to think of this is, what do you do when you carry a 1? Actually, you're going to have to continue carrying the 1 as long as you continue to see 1s up here. eventually you will get to a 0, and the carry turns it into a 1, and you're done. So this is our Turing machine for adding 1 to a number. All right? We have about 10 minutes left. I want you all to try a Turing machine which subtracts 1. So let's try f of x equals x minus 1. And I'm going to say you can assume that x is actually more than 1. If x equals 1, you should get 0. Of course, if x is 0, then you're going to have problems subtracting 1 from it, and I don't want to get into... There are ways to handle negative numbers and such, but I don't want to get into that. All right. Maybe I'll just, to help us get going here, I will think about some examples here. So here's a simple example. Subtracting 1 from a number which has a 1 at the end already, you just change that last 1 to a 0. So that's the easy case, right? What about, a harder example would be this. If there's a 0 at the end. In this case, you got to borrow, right? Remember how to borrow? I feel like I only vaguely remember how to borrow. And to be honest, I only borrow when I'm teaching this day of this class. In my ordinary life, like I'll probably teach this class again next year. I will not borrow between now and then. But yeah, so I will try to remind myself of how this is supposed to work. When you borrow here, first of all, tell me, what should the answer be in this digit? Should it be a 1 or a 0? Those are your choices. I think it should be a 1. The idea of borrowing is this 0 you somehow consider as if it were a 10, because I steal a 1 from a higher digit. And then it looks like a 10 minus a 1. Of course, in binary, that means a 2 minus a 1, which should be 1 as the answer. So the answer should be 1 here. And then what happens as I proceed to the left? Well, this 0 also got borrowed from, right? So this 0, when you do this subtraction, what should the answer be here?
1.
Also a 1, yeah. And then this one is the one which sort of its value was handed down. This should end up being a 0 here, and then everything else should be the same. So this is really, the only things that changed were right there. This is kind of like in base 10, if this was 100 minus 1, it would say 099. So in binary, it's the same. It's just you have 1s instead of 9s. All right. Anyway, see if you can write a machine that does that. It seems complicated on the surface, but actually your answer should look a lot like this. It's just the details are a little bit different. See what you think. I'll give you 1 more minute, and then we can talk about it. All right, your minute is up. Anybody want to tell me what you wrote? Maybe someone I haven't heard from yet today? I like hearing from different people. I see several people wrote something. Did I hear from you? I don't remember. All right, I'll hear from you again. I like you.
I don't know.
I like everybody.
I'm not sure if this is right, but I drew an arrow to the right.
Uh-huh.
10R.
10R. So this is kind of like the easy situation where the digit is already a 1. You're subtracting a 1. You make it a 0. I like it. All right, what else?
Then I drew an arrow pointing to itself, like in the middle state.
Yeah.
01L.
01L. Yeah, I like that. This is the borrowing step, all right? That means this is if you're in this situation when you see a 0, and you have to subtract 1 from it. First of all, the answer in this digit is a 1. That's why this 1 is here. And then you move to the left. That is to say you continue borrowing to the left until, and any subsequent 0 that you see, you also turn into a 1 until eventually you encounter a 1, which you turn into a 0. Excellent. I like that. Any thoughts about that? Anything else? Now I said assume x is greater than 1. What happens if x is actually equal to 1 here? Does this still work? If x is actually equal to 1, then this happens once. So if my tape, only has a 1 on it, what's going to happen? This step happens once. It moves over here to a blank. Then it goes BBL, so it's pointing back at the 1 in this step. It changes the 1 to a 0 and moves to the right. This turns into a 0. I think that works, right? So this still works if x equals 1. I probably meant to say that. Assume x is greater or equal to 1. It still works. What if x equals 0? What actually happens here? Now, this is something messed up is going to happen, I guess. Yeah?
It's going to create 1s going to the left.
Yeah, this will create 1s forever. So here, if x equals 0, then this makes an infinite amount of 1s moving to the left every time, because it's going to do this borrow step forever, moving to the left. So this makes something like it's infinite this way, and then actually stops at a certain point, like it has an ending over here, but not over here, all right? This is kind of like subtracting 0 and getting, subtracting like 0 minus 1 and getting infinity as the answer, something like that. You can imagine on a real computing machine, like if you've ever seen a mechanical calculating machine, which I happen to be an aficionado of mechanical calculating machines. If you try to do 0 minus 1 on a machine like that, the digits that you see are like little dials which have 0 through 9 written on them. If you start with 0 and subtract 1, the dials will all turn back 1 and you get 9, 9, 9, 9, 9 all the way across, which is actually exactly what this Turing machine does. So, obviously this is not useful if you really want a machine that can handle negative numbers. That's not what you want it to do, but this is not a surprising result from the point of view of a simple computer. All right, and I think that'll do it for today. Don't forget to send in your homework tonight. I'm going to be in my office for the next hour, so if anyone wants to chat about it, I would be happy to.